number 37, chapter 17, has to do with determining whether or not somebody has ESP. Anyway, there's 5 cards that are duplicates of 5 cards that are distributed randomly and equally in number in a deck of cards, and they have 5 different shapes on them. Usually this is done with an experimenter who holds the card up with the blank side facing the subject, and then the subject is supposed to guess which shape is on the other side of the card. So, since there's 1 out of 5 shapes, the probability, assuming that the subject does not have ESP, the probability that the subject guesses right is 1 out of 5, or 0.2, if they're just guessing. The probability of guessing wrong is 4/5, or 0.8. So, if the subject does not have ESP, then we expect the subject, on average, will pick 20 out of 100 correctly. Now, we don't expect every subject to get 20 out of 100, but we expect overall the subjects would get 20 out of 100. Now, but for this particular subject, we expect 20 out of 100. So this is a Bernoulli event. It's yes, no. The subject guesses right, or the subject does not. Assuming that the subject does not have ESP, then the probability of guessing right does not change. The population of guesses is infinite. There is no reason not to assume, and 3, as far as independent, that each ESP guess is independent of another. Now, we need the normal model in this. So, for a binomial, this is binomial probability because we have a set number of events, 100. I got this written down here. Okay, n equals 100, and we're concerned with how many successes occur within this set number of events. So this is definitely, it's Bernoulli, it's definitely binomial. It wouldn't be geometric because geometric does not have a set number of events. Now, you can be given a set number of events, but with geometric, we're only concerned with something happening once. All right, so with a binomial probability, the mean is NP and the standard deviation is square root of NPQ. So we have to consider 2 more preconditions in order to use the normal model. NP must be greater than or equal to 10. So that's 100 times 0.2, which is 20, which is greater than or equal to 10. And NQ must also be greater than or equal to 10. 0.8 times 100 equals 80, which is also greater than or equal to 10. Okay, so NP equals 20, which is 20 times 0.8. And then the square root of 20, we take, that's NP, so we multiply that by 0.8. And we get 16. 0.8 times 20 is 16. Square root of 16 is 4. So we have a approximately normal distribution of 20, 4. So let's just lay this out a little bit, because we don't know how many they picked. The question is, how many would they have to pick before we'd start to think that they might have ESP? So first standard deviation is 24, second standard deviation is 28, and the third standard deviation is 32. So if a subject picked 28 or more cards correctly, that would be 2 standard deviations above the mean, in other words, a z-score of 2. So the probability that z is greater than or equal to 2 is about 0.023. Now, probability equals 0.023 is so low that it is unlikely to occur randomly, assuming the person does not have ESP. Okay, so let me go over that again. Unlikely to occur randomly, assuming the subject does not have ESP. And so these results, the probability of 0.023, may therefore be evidence of ESP.